Hello everyone. Today we're going to be doing our first sorting algorithm, and this is the QuickSort algorithm. Now QuickSort algorithm is a very efficient sorting algorithm, and well, it's an in-place algorithm like selection sort and insertion sort, and it has a divide and conquer approach. Now, all these algorithms that we have been doing were greedy algorithms or dynamic programming, but this one is in a divide and conquer approach because it divides the problems into two subproblems or more, depending on the algorithm. I mean, in this case, it divides it into two subproblems, and then recursively tries to go back to its base case and then solve the problem using another method that's given. In this case, the partition method. Now, the algorithm, the simulation is pretty easy. It's really fun, but compared to other sorting algorithms, this simulation does require a lot of time to, get the hang of. So let's just look at the algorithm here. This is the QuickSort, the recursive call algorithm. Now, if this is the base case, if P is less than R, P is the starting point, R is the finishing point, and Q is the one that we divide the whole problem into two sets. Q is the middle part, the middle point. And this is the recursive call QuickSort A P Q minus 1. That is, this is the first part, divides it into first when it's divided once, and A Q plus 1 R is the second half of it. This is the first half and this is the second half. So let's look at the algorithm, the partition algorithm. First, we choose a pivot. Now, QuickSort can be done in three ways. It can have three kinds of pivots. One is the first element can be the pivot, the last element can be the pivot, or the middle element can be the pivot. For this example, we're going to be using the first element as the pivot. So here, X is the pivot. X is the pivotal element, so AP, and I is the pivotal index number. So I equals P. This is P and this is Q in this case, but in the whole algorithm it is P and R, and this is Q somewhere in the middle. But for this, since the parameter naming doesn't matter, we're naming it Q. Doesn't matter, you can name it R as well, but for since P and Q, we're just dealing with two elements only, two indexes only, so we name this Q. Anyway, let's move on to the algorithm. So first, I equals P. So for J equals P plus 1 to Q, in the beginning of the simulation, I would suggest that you keep the algorithm in front of you and then try to do the simulation, because you might tend to forget it. So let's move on to it. So 6, and then let's move on to J. J is this one, and then when AJ is less than equal X, that time I plus plus. Since AJ is not less than equal S, it's greater than X, so we don't increase it. So let's move on to the next J, which is this. 13 is greater than 6, so we don't increment I. So let's move on to the next J, which is this. 5 is less than 6, so we increment I, so I is this one now. And then after that, we swap AI and AJ. So this is AI and this is AJ. So we swap 10 and 5. So let's swap it. 5 here, 10 here. All right. So then we move on to the next J. Well, this J is still greater than 6, so we don't increment I. 3 is less than 6, so we do increment I. Let's move on to this, and then I is increased. So we swap, again, we swap AI and AJ. So 3 and 13 is swapped. This is 13 and this is 3. All right. So then let's move on to the next, let's move on to the next J, which is this. And then since 2 is less than 6, so we do increment I again. So I is here. So we swap 10 and 2. So let's swap it. 2, 10. Here's 2, here's 10. All right, so then again we increment J, and 11 is greater than 6, so we don't increment I. So now the next part is we swap AP and AI. I'm sorry for the handwriting here. You can check out the proper algorithm within your textbook, or in any of the, if you just search in the internet, you can get the QuickSort algorithm properly. We swap AP and AI, and AP is what? This one, that is X, and AI is what? This one too. So 2 and 6 we swap. So let's swap it. Here's 2. So 2, 6. And then we return I. So now we make this the dividing point. That means we return I to here, to Q, because this is a partition method here. So now Q is the dividing point. So there will be 2 divisions. One is from A, P, Q minus 1. So 2 divisions recursively, like a binary tree. 2, 5, 3. And another is 8, 13, 10, 11. And the first element is always the pivot. Let's change the color. Yeah. All right. So the first element is always the pivot. 2 is the pivot here. So again, we do the partition method here. Now x equals AP. This is x, and this is I. This is j. So we we move on to the algorithm. If aj less than equal x, well, j is not less than equal x, so we don't increment I. So then we move on to the next j. 3 is greater than 2, so we don't increment I again. So we swap. So we don't need to go to this swap process either. We don't, because we don't enter this if function at all. So we go to this swap, AP and AI. So AP is this and AI is also this. It's the same thing. P and I are in the same position, so we don't need to swap it. So now we divide it into 2 parts. Well, we just get one part here, 5 and 3, because 2 is already here. And then for this one, we have to do, like when we're doing recursive calls, just remember that all these steps in one level are done at the same time. You don't finish. I mean, when you think about the computer wise, how the computer does it is that they solve these 2 sub problems at the same time. They don't solve like it's not like they solve this one whole tree and then after they're done with this tree, then they go to the other tree and solve. It's not like that. So it's better when you do the simulation, that time also you have this good practice of solving the 2 parts of one tree, I mean of one level of a binary tree at the same time. All right, so here this 8 is the pivot. All right, so this is x and this is I and then j. So j, well, this is greater than 8, so we don't go to the if function. And then again, j, this is greater than 8, so we don't again increment it. And again, this j is greater, so we don't increment. So p and I with the same position, we swap AP and AI. I'm sorry if I'm going too fast. It's kind of hot in here. Anyway, so we swap p and I, AP and AI, and well, it remains the same. So we divide this tree into 2 parts. Well, we just get one part, 13, 10, and 11. All right, so let's do this let's do the call with this part. Here it's x, I, and j. Well, j is this part, aj is greater than, I mean, it's less than x. So we increment I. So we swap, I mean, we increment I, and then we swap AI and AJ. Well, AI and AJ are the same thing, so we don't need to swap it. But we do have to swap PAP. This is AP. AP and AI. So we get, what do we get? 3 and 5. So let's swap. Here it becomes 3, here it becomes 5. 3, 5. All right. And let's do it for the same, let's do it for this one also. Let's just change the color. It's getting bored of this color. All right. So 13 is the pivot, and then it's x again. I mean, x is AP. Anyway, x, and then this is I, and this is j. Well, j is, I mean, AJ is less than x, so we increment I. I comes here, all right, and then AI and AJ. We swap AI and AJ. Well, AI and AJ are the same thing, so we don't need to swap it. So we move on to the next j. Again, I is incremented. Yeah, I is incremented because AJ is less than 13. I mean, 11 is less than 13. So I is incremented. I comes here. We swap AJ and AI. Well, AJ and AI are in the same position, so we don't need to swap it. So then we swap AP and AI. Here it's AP and this is AI. So we swap 13 and 11. So let's swap it. 13 and 11. This becomes 11 and this becomes 13. All right, so this is the I, we return I, so this 11 and 10 is divided again. So 11 and 10. Now 11 is the pivot, and then x, so I, j. Well, AJ is less than x, So we swap AI and AJ. I is incremented. We swap AI and AJ. It still remains in the same position. So then we swap AP and AI. Well, AP is this and AI is this. So 10 and 11 we swap. So this becomes 10 and this becomes 11. All right. So this is the final one. Now let's try to arrange this tree. Let's try to arrange this tree. First comes 2, and then comes, like, to try to see it in this position. So 3, and then we have 5, and then we have in this position 6, and then it's 8, and then it's 10, and then it's 11, and then we have 13. All right, so this is the final answer. This is the final sorted output. As you can see, it's sorted in ascending order. So yeah, that's about it for this simulation. Whenever there will be a question that you have to do the partition, try to understand the algorithm. You have to, if they say that you have to do the partition till the second recursive call, I mean the second partition call, it goes to up to this level. And then if it's just third partition call, it just goes to up to this level. Don't do it more than these levels, because maybe they'll cut marks. If there's a question like that, just like do the simulation of the quicksort algorithm up to the second partition call. Well, this is the first partition call. This is the first partition call, and then this is the second partition call. And this is the third partition call. This is the fourth partition call, fifth, sixth, likewise. All right, this was the whole algorithm too, and the analysis of the quicksort algorithm is, well, let's look at the analysis. Quicksort analysis. All right, so the quicksort, this quicksort is order of n square in the worst case, and it is order of n log n in the best case. In the worst case, it's order of n square because it becomes n square. It becomes the worst case in what situation? When it's fully sorted, or when the pivot is the highest element, I mean the highest value element, or the lowest value element. That time what will happen? That time the tree will be slanted in one way. That means in this way there will be no tree growing. It's gonna be in this one way, like this one way that we have seen. There was no element here. We just had to do it here. So this whole the whole tree will be in a slanted way, and there will be no element on the left side of the tree, binary tree, if it's a binary tree. So that's why it will be order of n square. But otherwise it will be order of n log n, because, well, as we can see, there's always 2 divisions most of the time. I mean, you can just, like, it can be negligible ones, but most of the time it has two divisions, 2 recursive calls. So the height of the tree is log base 2 of n, and the number of leaves is n. So the whole complexity is order of n log n. So yeah, I hope you understood the tutorial, and please like and subscribe if you want more CS tutorials, and, well, good luck.